Okay, so this problem is a little more difficult than the original problem. Because in the original problem, we knew that you couldn't have more than 8. And if we got to 8, we knew we had the right answer. On this problem, we don't know what the minimum number is. And so if we get a number, we don't have any way of knowing that we found the smallest. It does turn out to be 5. And there are lots of ways to organize it to get 5, but there are also lots of ways to organize it where 5 won't work, right? There's lots of ways that 5 aren't enough. In some of these solutions of 5, you can have 2 queens attacking each other. In some of these solutions of 5, you don't have 2 queens attacking each other, and they can work. But 5 does turn out to be the smallest number. All right, but this problem is, again, there's not a clear-cut way to know. How do you prove that 5 is best possible? You have to prove that you can't do it with 4, or 3, or 2. And we know we can't do it with 1, because we know there are places on the board that 1 queen can't reach. But how do you prove that 2 don't work, or 3, or 4? All right, so this problem is a problem that's known as domination. At least in graphs, it's called domination. So the idea of a dominating set this is a set of vertices in the graph So a dominating set is a set of vertices so that every vertex in the graph is either in S or is adjacent to a vertex in S. In the context of chessboard or Queen's problem, every vertex either has a queen on it or can be attacked, right, reached in one move by one of the queens. Often you see this described in a context like this. So if we look at the house graph that we had seen before, we want to find a set of vertices to represent placement of fire alarms. And a fire alarm can detect a fire in that room or in an adjacent room. And so ultimately what do we want to do with domination is we want to make this set as small as possible. So the question would be, what's the minimum number of alarms that we need in order to be able to detect all of the fires?
Isn't that, I heard from someone that that's what you wrote your...
Well, there's a variation on that we'll talk about. Yeah, my doctoral thesis. We'll talk about that in a few minutes, just as a variation on this problem. So what happens in this particular graph? How many fire alarms would we need in order to be able to detect all the fires? Not where they are, but just that there is a fire. Where would you want to put them? Let's label these. A, B, C, D, and E. B and E. All right, and that would work, right? B and E, if there's a fire anywhere, that one of these alarms, maybe both, would go off, right? Because the alarm's going to go off if the fire's in that room or next door. All right, so dominating set is just a set. So what could you have? You could have alarms everywhere. That would be a dominating set. But if we wanted to find a minimum dominating set, we're trying to have the smallest set of alarms that works. All right, so minimum dominating set, or the minimum domination problem, as a decision problem, would say here's a graph and here's a number. is there a dominating set of size no more than that number? Right? And so it'd be a yes or no kind of question. What does that correspond to on this? Remember we said that the graph that you can draw from the queen's is lots and lots of edges everywhere, right? So we don't really want to draw the graph that corresponds to an 8x8 queen's board. But there is a corresponding kind of thing. And once you put a queen on there, then it can attack all the places that that queen can reach. And basically you're trying to make sure that every vertex is either in the set or is adjacent to something in the set. All right, so minimum domination would have an instance of graph G and an integer K. All right, now the idea of this is we don't know the graph or the K. So our algorithm that we would be looking for can't know that information ahead of time. If we can know that information ahead of time, for a particular problem, we can solve a particular graph, but this is an algorithm that we would be looking for in the general scenario. Okay, so our problem, minimum domination, first of all, let's show that this problem is in class NP. So how would we show that it is in class NP? We have to be able to describe how to check a potential answer. All right, so what does it mean to check a potential answer? If we have a graph, maybe it's the queen's graph, and maybe our K that we have decided is 5. How would we check a potential answer? How would we check Kyle's answer? We would take his solution and start looking at other vertices in the graph to see, is this vertex adjacent to one of those 5? Is this one adjacent? Right, we check to see, are there 5 in his answer? Right, 5 vertices. And is everything adjacent to one of those, or else is it one of those? What's the worst we have to do? We have to check a bunch of edges, right? So we have to check a bunch of edges to see if there's connections between them. So it depends on how we represent the problem. Also, is part of this issue, but we can just check to see, does everything have an adjacency in his 5? If it doesn't, is it one of the 5? And that's how we would check, right? And so the problem is in class NP. We can check and answer pretty quickly. What if it's not an actual answer? If it's not an answer, we would find out, oh, wait a minute, you didn't attack this square. Or no, you have 6 queens rather than just 5 queens. Or something, right? We would have an answer to the question. All right, so a potential solution can be checked quickly. All right, so the next part is we need to transform a known difficult problem into this one. And what we're going to transform is we are going to transform we're going to transform the 3 C and F SAT problem to this. Okay, so the process for showing how to transform something is we show how to start with this problem and turn it into that problem. So that if this one had an easy solution, so would this one. All right, so let's look at an example of 3 and I immediately started writing this in ands and ors in this way. I apologize, instead of writing out the words. There's an example of an expression that's in 3 SAT. I just wanted to have enough pieces to show you what's going to happen. All right, so here's what we do. We create a triangle for each one of our variables. And its complement. Even if we don't have the complement showing up in the graph, which actually this time we did, but even if we didn't, okay, so we can automatically do that, right? We can do that quickly. We can create a triangle. Even if we had 1,000 variables, we can create 1,000 triangles. All right, so that's not going to take much time. Then we're going to create a vertex for every clause. So this is the first clause, and we're going to draw an edge to the variables that are in that clause. Second clause. Like that. And third clause. Not x2 not. You're right. I put that in the wrong spot. There we go. Is that right now? All right, so now what happens? Now we've turned this problem into this problem. What were we trying to ask with this question? We were trying to say, is there a way to assign the variables x1, x2, x3, and x4 so that this thing is true? Does that make sense? In the graph problem, the question is there a dominating set of size less than or equal to 4? All right, so what do we need? We need a dominating set. Means that we need to pick vertices to be the ones that we care about, right? The fire alarms. And we need them to be, at the end, we need everything to be adjacent to one or the other. We need everything to be either in that set or adjacent to something that's in that set. All right, so let's see if we can figure out how to create a dominating set here. What are we going to have to do in each triangle? We're going to have to pick something from each triangle, because otherwise the top of the triangle won't be dominated. And when we pick something from each triangle, that will dominate the whole triangle, but then we also need to make sure that all of the clauses get dominated. All right, so do you want to pick x1 or not x1? Pick not x1? No, should make that red. Not x1. All right, so now what has been dominated? This has been dominated, this triangle, and that clause over there is okay. Right, that vertex. What about from x2 or not x2? Right now we're just kind of picking something, right? Which one do you want to pick as being true? Which one do you want to pick for our dominating set? Pick x2. So now what do we have? This triangle's dominated, this triangle's dominated, this clause, and this clause are dominated. What about over here? Pick x3 as an example. And in the final one? The final one, it doesn't matter in that particular choice. All right, so does this graph have a dominating set of size 4? It does. What do the red vertices correspond to in terms of the original problem? The red vertices could be the things that we have made to be true. So here, not x1 is true. That means x1 is false. x2 is true. This is false. But what is this whole parentheses? This whole set of parentheses is true. All right, let's look here. This is false. That's true. x4 was false, but this is still true. What about over there? We have true. We don't have to keep going, right? We have true. They're all true in that case. So what happens for the whole expression? The whole expression is true. Is there a solution to this problem? Yes. Is there a solution to that problem? The answer is yes. What is the solution is a different part of it, but the solution of yes corresponds to a solution of yes to the original problem. Does that make sense? So
I didn't catch how you got to transforming that to the normal form. Like, how did you get to writing out the
like this line,
yeah,
I made it up. I just made up something that was in that form. Right? So we just started with an example of a problem that was in 3C and F, and then said, how would you turn this into a graph problem? Right? So what happens then? Any potential 3C and F problem you have, what could you do? You could turn it into this graph problem.
So that doesn't necessarily relate to what we're doing right now. That's just an example.
Yeah, this is just an example. The idea that we care about right now is the transformation. Given one of these, how do you transform it into the graph problem? So what do? You create a triangle for each variable. One node corresponds to that value being true. One corresponds to that value being false. The other is to force us to pick one of those. And then you connect these vertices that represent clauses to the correct pieces. All right, so what happens? Every 3C and F problem, every 3C and F SAT problem, can be converted into a corresponding domination problem. So what does that mean? That means that the domination problem is at least as hard as the satisfiability problem. Because if we could solve the domination problem, we could solve the satisfiability problem. If we could solve the satisfiability problem, then we could solve all of the other problems in class NP. So domination turns out to be as difficult as any of the others. So domination, this minimum domination problem, is in class NP. Make sense? And that's the typical progression. We show that our problem is in the class. We show how to check an answer. And then once we've shown how to check an answer, we take one of our known hard problems and transform our known hard problem into that new problem. So our new problem then is at least as difficult as the existing one. So if somebody could figure out how to solve the domination problem, guaranteed in a polynomial time for every scenario, then we would be able to solve all these other kinds of problems. So some of these other kind of problems relate to things like, would solve problems for companies who want to solve logistics problems and be able to move things as cheaply as possible. It would solve a whole bunch of other kinds of scenarios that people want solved. It would also, unfortunately, solve some problems that are used in cryptography that people don't really want solved. So there'd be a trade-off, right? It's like, oh, we would like to have that solution to be able to solve these problems, but we really don't want there to be a solution because that means we solve these others as well. The kind of things that we don't want to have easily solvable. Again, the transformations might, in real life, end up taking a really long time. They're polynomial time, but there might be a long, it might be physically still outside the realm of possibilities. But what happens again, every time we come up with a solution, polynomial time to something, people tend to come up with something even better, down to whatever the best possible answer happens to be. So that's how we show that a problem is a hard problem. We say, hey, look, here's another hard problem that I can transform into this new problem that we're looking at. And this new problem that we're looking at then must be at least as hard as the other one. All right? And so domination is one of it. Conceptually, not difficult. Right? We're just trying to say, here's a graph. Let's fill in some of the vertices around so that we have everything is either filled in or is adjacent to something that's filled in. And we're going to try to make that as small as possible. So we could show a domination problem to a little kid. Right? A small child can color in dots and count and say, oh, yeah, look, everything. But so it's not the conceptual part of that problem. It's something else about it. Right? Somehow trying to figure out how to come up with an algorithm that in any situation could take any graph and any number and tell you whether there's a dominating set that has that many vertices or fewer. Okay, so
So that last problem, when you're like picking the vertices to like make your dominating set, do you have to pick vertices that are labeled?
If you don't pick vertices that are labeled, like if you pick some of these, then that means that you're not counting these.
Okay, like
So,
a really high K.
so your number is going to go up, right? The idea of the K that comes with this problem, the K that comes with it is once you have your example, or once you have your instance of the situation, your K is how many ever variables there are in terms of the variable and its complement are counted as one, right? So how many ever, so you want the K gets determined by the expression that you give it.
Is that why each variable turned into a triangle so you can't pick the bottom?
Yeah. And that's the particular purpose, right? So you turn it into a triangle so that you don't pick these, and you turn it into a triangle so that you're forced to pick one of the two and not the top one, but you have to pick one of them. If you pick the top one, what does it correspond to? Picking the top one corresponds to, like what would have happened over here, corresponds to, it doesn't matter which way you set that to be true or false. But you have to pick, well, you have to pick something from each triangle. Right? So the structure of this is forcing you to pick something from each triangle. And then that way, that answer can be converted back into an answer for the original problem. It turns out that in other scenarios, maybe there are lots of things that we transform 3C and F SAT to those problems, that sometimes these things are much more complicated, or sometimes the process is much more complicated. This particular problem of domination turns out to be one of the easier kind of transformations to see visually. Some of them are really complicated. Some there's no pictures that go with it. Some it's some other kind of way I'm describing. So there's just a variety of how you go about the transformation. But the behind-the-scenes process is the same. You take a hard problem that we know is hard, and we turn it into our problem. So what have we described here? The general guideline of how to turn something like that into a graph. Now, in this particular example, it didn't really matter. We could kind of guess our way through and end up solving the problem. Often, it's a lot more complicated than that, right? To try to figure out which ones should be true and which one should be in the dominating set and which one shouldn't be. Does that make sense? Okay. So, since we're at this point and we have just a few minutes left, let's talk about a variation on domination. Variation on domination is called an identifying code or identifying codes. So here we have this graph. Rather than just trying to find out, is there a fire somewhere, the goal is to place the alarms So again, the alarms still can detect a fire in their room or next door, but they don't distinguish whether the fire was in the room or next door. Right? It just says, hey, there's a fire close by. And so the alarms go off. And what we want to do this time is we want to place the alarms in such a way that we don't have just, oh, there's a fire, but we know exactly where the fire is. All right, so what do? We went this way. All right, so let's see where we can put alarms in this graph, where again we're selecting vertices for the set, to see not only that there is a fire, but where the fire is. So where do you want to put some alarms? B and D? All right, so let's see what happens. If we put alarms in B and D, all right, so if the fire is in A, what happens? B is going to go off. What if the fire is in B? Then just B is going to go off. So at this point, what do we have? That's not enough information. Because if the alarm in B goes off, we don't know where the fire is. But let's keep on going. What if the fire is in C? Then B and D go off. If the fire is in D, then just D goes off. If the fire is in E, then B and D go off again. Right? So what do we have? If the only alarm or the only location that we know is if alarm D goes off by itself, we know the fire was in D. Right? But otherwise, we don't know where the fire is. If alarm B goes off by itself, we don't know whether the fire was in A or in B. If B and D both go off, we don't know whether the fire was in C or in E. So what do we need to do? We either need more alarms or we need to move them around. Does that make sense? All right, so what do you want to do? Use more alarms? Where do you want to put a new alarm? Or do you want to move them and get more? I mean, put it where? Put it in C? All right, so now what happens? If the fire's in A, then it's still just alarm B. What if it's in B? Now B and C go off. What if it's in C? B, C, and D. If it's in D, C and D go off. And what if it's in E? Just B and D. So now what happens? Now we have different sets here that will determine, so you know from the set of alarms that go off, which room was it in. All these sets are different, so this gives us a solution to the identifying code problem. These three vertices will detect and locate every fire. Could you do it with smaller? So that's the minimization version of it, right? A minimum identifying code says, can we do it with fewer alarms or fewer vertices in the code? And that's the other part of the question, right? Turns out in this particular case, no, we need three of them, right? And these three will work. Is this the only three that will work? No, we can move them around a little bit. But there are certain sets of three that won't work. What if I move that one up there? What if the fire is in one of these two places? Then both alarms go off, right? And it doesn't tell us where it was. What if we put that one there? Does that work? Which alarms go off if the fire is in A? B and E. What if the fire is in B? B and E. All right? So there are some things that work, some things that don't. That'll be okay. Tear down the whole house. Right? So there are a couple of solutions in this particular case where three work, but lots of solutions or other solutions where three won't work. Two never work in this particular situation. Yeah, so this is my doctoral thesis was on this topic. It was actually rather short, 65.
You got 65 pages out of that.
So here's what happened on this problem. I went to a conference, and the person giving the talk was talking about putting fire alarms in places and so on. And so I started drawing pictures and kind of quit listening to his talk. In his talk, he said, and I just didn't hear, that his alarms were three-state alarms. They could tell you whether the fire was in the room or next door or that there was no fire nearby. So they had like heat detection or something as well, right? It's like not just smoke, but heat. So it's like, oh, there's a fire, but it's really close. Or there's a fire, but it's next door somewhere. Or, no, I'm not detecting any fires at all. My alarms here, these alarms were two-state, right? Fire close by or somewhere close by or not. His alarms were three-state. I ignored that part. Well, it turns out that his three-state solution, or his three-state problem, had been well studied, and he was describing that three-state solution, and that was perfectly fine. But the two-state solution, the two-state alarms, hadn't been so well studied. And so by ignoring the actual problem and paying attention to the motivation, I was able to get a doctoral thesis out of it. At the time, there was one other group in the world working on it. There was a small group in Finland working on the problem. And they had made a lot of progress. And then I made my tiny little contribution, and now there's a bunch of people around the world in different places who are working on that problem. And in terms of actual real-life applications in networks and so on, being able to detect errors and problems in networks. The happiest I've been from my doctoral thesis was finding that someone had used some of the results to describe a manufacturing process, and being able to determine in the manufacturing process where something, like on a yeah, I don't know if it's exactly in terms of an assembly line, but you can imagine it on an assembly line. Where on the assembly line should you check for errors? Not necessarily checking at every step, but checking to see, okay, wait a minute, there's a problem here. Where did that problem come from? And so it was kind of cool that someone used those results in a completely, actually, I had indicated that you might be able to do something like that idea is like a motivation, and they found a way to actually apply it. So that was kind of cool for me. So what happens? The identifying code problem is domination with an extra twist, right? You have to have the dominating set plus some more stuff. And it turns out, again, this problem is just as hard as the others. Right? So this problem is also in the NP-complete realm. I didn't get to prove that because the people in Finland had already proved that this problem was one of the hard problems. But instead, I found my little pieces for it. Anyway, so what's the idea? That sometimes taking an existing problem, sometimes it pays off to not really pay attention. Not usually. Don't take that as. But in my particular case, by not really paying attention, and then at the end of the talk, I'm looking at the answers I'm creating and looking at the answers he has, and I'm like, I don't get it. And it was a while. Then I went back home and talked back and forth with him for a while, and they had written he and a couple of other people had written a book, and I got access to the book and finally figured out that exactly what the distinction was, and so anyway, that's the little contribution. So anyway, so what happens when you can't solve one of these problems, right? What happens when you have one of these NP-complete problems and you really need you need an answer? We know that there's probably not a polynomial time algorithm for it, right? If there were a polynomial time algorithm for one of these, somebody probably would have come up with something by now. And even if there is one, nobody has come up with one yet. So if you are tasked with solving one of these problems, what do? You are working later in some programming job, and your job is to solve one of these problems. What would you do if you were in that situation? So often what we end up doing is, first of all, recognizing that our problem is one of those. So there's sometimes some work that's necessary, but recognizing, this is a really difficult problem. Not difficult just because I don't know how to solve it, but difficult because no one knows how to solve it. And so often what we do is we solve specific types. So for domination, for instance, in certain kinds of graphs, it's not a difficult problem. In certain kinds of graphs, we can easily solve domination, even in linear time in some scenarios. So sometimes it might be that we can solve specific cases that will cover whatever physical, real-life kind of thing we have to deal with. If not, then we instead will often try to develop or use approximation algorithms. Right? So sometimes there are approximations that we can guarantee that will be within a certain percentage of the real answer that we're looking for, or whatever, if it's an optimization kind of thing. If it's something else, then sometimes we can, again, still modify the problem a little bit and come up with an answer to the modified version, which isn't really the answer we were looking for, but it might work for the scenario or for the cases that we need. And sometimes we do use that last solution and just do what we have to do, right? All right. So what do we really do? You try to do the best you can, right? If you're stuck in a situation of a really difficult problem, we solve it as well as we can. And sometimes that means that we're only able to look in particular places, or we only get a kind of good answer. And sometimes it means we can't do anything about it, right? We just have to go on to something else. All right.